to go over the graph part, so we went over eliminating the parameter on your homework. So that part should have been done on your homework. But then we went into the ones with the trig functions. And we said you could graph this in your calculator using your parametrics, and you would see a graph of an ellipse or a circle or a hyperbola. And then when we converted it to a rectangular equation, you would actually see the equation of the given ellipse or circle or whatever that happened to be. So is everybody comfortable graphing these on your calculator?
So when it's sine 2, that just turns into the square?
2 theta is still the t. It's still the parameter on this. Whether it's 1 theta, 2 theta, 5, it's still a parameter. It's still going to go in a circular path, so we can treat that as t. We don't have to worry about the double angle on this. It actually would take half the time. You don't have to worry about your double angle on this. We're just going to consider this where your parameter is. This is t. Okay? So now, we're going to graph this, and for those of you that weren't here yesterday, or didn't do this, and doesn't understand it, we're going to graph these just like you read them. This one was the reverse of what we normally say we have, but we'll just put the t in here just because that's the parameter for this. And 2 cosine t. Okay, when we graph this, your table, your window has to go just like the angles do, from 0 to 360, so that you can get the whole thing of the ellipse or the circle and whatnot. It doesn't matter in this part, it'll like work itself out to this part. And your mode has to be degrees if you set it to 360. If you do too high, then set it to radians. So we graph this, and we should see an ellipse. Okay? This is in your parametric mode that we see this ellipse. Can everybody graph this? Okay. From there, we said, okay, algebraically, we're going to eliminate the parameter. And how do we do that? We solve for that parameter in terms of x. And then if it's a regular equation, we plug it into the y. But because these are 2 trig equations, we're going to solve for the x, for the parameter in terms of x, solve for the parameter in terms of y, and we're going to use an identity that we had for trig to help us convert this to a rectangular equation. So we divided both sides by 4, divided both sides by 2, plugged it into this equation, and you could see your ellipse coming. Right at this point, this is your A, this is your B. It went up 5, down 5, over 4, probably a lot more this way. Well, whatever. A lot more on the y than almost a circle. And there's your equation of your ellipse. The nice part about this on your graph is you can see this. Here's the y. Is the y not 5? Oh, the y is 2. That's why I'm off on this. Yeah. The y is 2. So the y is going up 2, and the x is going over 4. So you see it here before we even square it. There's your a and your b. Once we square it, that's your a squared, b squared. But before we square it, the 2 is the 2 that's up here. That 4 is the 4 that's across your x-axis. The y equals? You use your parameter. Don't put a 2 there. You want to solve for t. You want that to be your parameter. Okay. So that works out for that one. Okay. The rest were all basically the same. The only difference you had to do is get this by itself. So sometimes you had 2 steps. You had to subtract 4 first. You had to add 1 to this guy first. So we solve in terms of your parameter. And if it's helpful, keep it over 1. I like it over 1. This way you know that that's your ellipse. You're going to plug it into your cosine squared plus sine squared equals 1. Doesn't matter if I do sine squared plus cosine squared. Doesn't matter if I change the order. It's commutative property. I can put any order I want. What drives the ellipse is the larger number in the denominator. That's the major axis. You should be able to graph the parametrics, the set of the parametric equations, in your y equal. Can everybody graph those? And then we should be able to algebraically eliminate the parameter and convert it into a rectangular. We call it a rectangular equation. A regular equation that we know and love to be an ellipse equation. You can find your center, 4, -1. You can see that your x here, above the x, it's going over 2. Your y, up and down 1. Before you even square it, there's your a and your b. They all basically work the same. Solve for the cosine, solve for the sine. Plug it into sine squared plus cosine squared. There's another ellipse. This ellipse, the y was the major axis because the y was greater in the denominator than the x. So you can see a vertical look to your ellipse. And everybody can graph this in parametric mode. Okay, and eliminate the variable. Yes. The next one might have been a little trickier. This one, we're dealing with the secant and a cotangent. And you can absolutely graph this. Did anybody have trouble graphing this? Anybody have trouble with the graphing of this? Okay, for secant, how do I say secant in here? Not inverse cosine. Reciprocal cosine. 1 over cosine. Okay, and then you're going to put your parameter in.
I was wondering, couldn't you also just have done cosine 4 over x, or would that not have been okay?
Cosine 4 over x? No. That isn't, no. And then the next one, we've got a tangent key, tangent parameter. When you graph this, there's your hyperbola. So we know when you come up with this equation, it's going to look like an ellipse, it's going to be equal to 1, it's going to have a minus in the middle. And which axis is going to, which one's going to come first, x or the y? X. How come? It's not bigger, I don't care about it. Excuse me? X comes first, why? Because that's where your parabola is vertex at. It goes off the x-axis. Thank you. Okay, so now, in order to do this, guys, we're going to, again, solve for your parameter. Solve in terms of secant, solve in terms of tangent. Your regular formula, your Pythagorean identity formula, if we take this and we want to make a tangent, got the word tangent in here, and we have to divide this by cosine squared. If I divide everybody by cosine squared, I get 1 plus tangent squared equals secant squared. And that's the identity I want to use. So you just plug in your pieces again, square them, and obviously it has to be equal to 1 when you do a hyperbola or an ellipse. So move this guy over, subtract it from the other side. And didn't your x come first? Because it came off your x-axis. Was this the tricky one? This was probably a little trickier than the other ones. Because you had to sign in the
Yeah, this
cosine
one
squared.
was the hardest.
Yeah. Are we okay with this one now?
Yeah.
Okay.
Number 20.
Okay, and then this one was a circle.
This one was easy.
Yeah. Use your circle formula. The other ones are pretty much already set up like that when we do the ellipse. They're almost in your circle formula every time we do this. It's just that when you set up the other ones, what happens in an ellipse is like this guy. It's very close to your circle formula, isn't it? The only difference is right here. Your radiuses are not the same. There's no radius for this because your ellipse doesn't have the same, underneath the y and underneath the x. If it did, it would be a circle. So it's got the same set of formats that this does, only this comes out to be a circle because your radius is the same. R is the same for both. Still, you're using cosine squared plus sine squared. And if you left it like this is not wrong. This is an ellipse, but it's a special ellipse. It's your circle. And then you can multiply both the old terms by 16 and put it in the format of a circle. You can graph this the same way you graph the other ones. Questions on this? Can everybody do these?